Elasticity is a nature of the objects, right? Whenever their shape is changed, they will try to restore, okay, restore their original shape. So, in the sense, whenever the elasticity could be like when a body is subjected to what is called as deforming force. Internally the body develops a restoring force. Okay, so restoring force gets developed. This is inside, okay, inside the body. So this particular feature is what we call as the elasticity. Now this particular force which is developed internally, we have a standard way to measure that. Okay, so that is what is called as a stress. So first let's define a stress, right? That is this restoring force developed inside a body, right? Inside a body, in the sense subjected to deforming force. Body subjected to deforming force per unit area is called as stress. So stress is the internal force per unit area. So in 1 square meter of the body, how much internally force gets generated? So by laws of physics, by the basic laws of physics, we know that this force which is getting developed is always equal in magnitude but opposite in direction to the applied force. So this stress is equal in magnitude and it is opposite in the direction to the applied force. The applied force is already, we know that it is called as deforming force. So whatever force we apply, there is reverse force developed inside the body called as stress. Now how do you measure this? So this is force per area. So we can call stress as the force per area, that is F by A. So this, what is the unit? Force is in newtons, right? Denominator is area. Area has meter square, but you write it in the numerator as Newton meter square. Okay, so that's how you try to measure this. Now compared to the stress, there is another quantity called as a strain. So let us try to define the strain. Whenever a body is undergoing a deformation force, and there is an internal force to restore its original structure, always you see that the body may not get back to its original shape. There may be small change, right? Originally it was having some area, it was undergoing some deforming force. Because of the deforming force, now you have the body's shape getting changed, but internally there is a stress getting generated, and stress tries to restore its original shape, but right, because of the physical nature, right, always it will not come back to the original shape. There is a small change with respect to the original dimension. So what you call, we define a strain. This is the ratio of change in the dimension of a body, certain body which has changed its shape to the original dimension. It can be change in just length. Previously you had length like 4 meters, but after the deformation force and the stress getting acted upon, it gets restored to 3.9 meters. So you see that there is a change of zero point 0.1 meter whole divided by 4 meters. So that ratio is what is called as the strain. Okay, so original dimension. So you see that it's the ratio of the same units, like meter per meter. So this is the strain is unitless or dimensionless. So strain is unitless. This is because I'm dividing the same thing, meters by meter. So meter will cancel. So it's a unitless quantity. Okay, all right. So we understood the basics required to define stress and strain. Now, so let us try to look at the various types of stress and strain. So first one, we'll start with the types of stress. Types of stress. So first type of stress is called as a normal. This is normal stress. Now, the force is applied normal to the cross-sectional area of the body. In the sense, whatever deformation force you are going to apply, right, that is going to be applied 90 degrees to the surface area, right? So that is what is called as normal stress. So if force is being applied, force is applied normal, or this is perpendicular uh, to the cross sectional area of the body, right? Then whatever is the restoring force that is developed per unit area of that body is called as normal stress, or it is also called as the longitudinal stress. So remember, force is applied 90 degrees to the surface area. This is the basic plan. If that, in that case, whatever is the internal force that is getting developed is called as this. Okay, so okay, I'll finish the sentence. Area of the body, then the this is restoring force, restoring force developed per unit area is called as normal stress. This is also called as longitudinal longitudinal stress. So the best example we can give is like this. Let's consider a situation wherein we have, this could be the ceiling of certain place. So we have say some, let's say there is a wire. This is a wire, and it has certain cross section. Okay, and let us say this wire is being connected, say like this. Okay, it's actually hanging from one of the points. And now let us say that it originally, so I'm actually trying to apply the force like this, perpendicular to the surface area. So what I do, I apply the force in this direction. So you see this is normal, 90-degree, right? So this is the normal stress. So you know that this is a given area of cross section. So I will call that area as A, right? So let's call this as the wire. Let's say that originally, right, you had a length, let's say it was up to this point. Let me assume that originally this wire, before you applied the force, it was still here, and now the length has been increased till here. Okay, now this is how we always try to represent. So this is the initial length, and after that it actually changed its length like this. So mathematical notation for this representation should be, originally I had a length L, and later on it changed its length by delta L. Okay, so you see that there is a change of delta L by L, that could be the strain of this. Okay, now let's go ahead. There is a normal stress which is defined in the following fashion. Now let's say that there is another type of the stress. That stress is called as shearing, shearing, shearing stress. So the shearing stress is something like the restoring force per unit area developed due to applying the tangential force. So whatever force you are applying will be tangent to the surface area. It's not like the normal to the surface area. So we apply the force, that is a deforming force. If a deforming force applied or uh, is applied uh, parallel to the surface area, parallel or tangential, okay, to the surface area, surface area, right? The restoring force per unit area, okay. The restoring force per unit area developed inside the body is called as the shearing stress, also called as the tangential stress. So we can call it by any name. So let's try to write a notation for this. Okay, so let us try to initially let us try to draw a rectangle. So we'll copy this rectangle, say here. This is the original shape. Now let me connect them properly. So see, this is the initial structure. Okay, initially this was like this, let's assume, but after I apply a certain amount of force, let me assume that this slightly bends. Now let me change the color to show the change in the dimension. So this is the newly applied force. So because of this, now everything changes. So you can see that the newly formed body is like this. There is a change in the dimension. So that is what we try to denote now in this fashion. Okay, so it's actually this red colored line represents the new shape after we apply make there to be applied with some force. Okay, all right. Right. Now I can see that there is a change in the shape. The movement of this particular body is this much. There is a change in the shape. We call this is say delta x, right? And the height is not going to change. This height, whatever you have, is still same. But what changes is there is an angle that is denoted by theta. So this angle is what we call as theta. So I can see that tangential to the force, right? So force applied is in this direction. So you can see that the force is normal, not normal. The force is tangent to the surface. So this is the surface. To this surface, I have applied a force tangential, right? That's why whatever is the force that is developed inside this body, right, is called as the uh, shearing stress. All right. Now let's go to the types of strain now. Types of strain. So first one is longitudinal strain. So how to define the longitudinal strain? It is straightforward. So we know that strain is nothing but the ratio of change in the shape to the original shape. Okay, so it's a unitless quantity. So if you want to measure the longitudinal strain, I need to take the ratio of change in dimension. So in this case, it's in one dimension, so you call it as a length. So it's a ratio of change in length. Change in length. So let's denote that as delta L, right? To the original length. So that is L of any given body is called as longitudinal strain. So we will call therefore the longitudinal strain is equal to delta L divided by L. That's all. Okay, first type is over. Next, the second type of strain is called as shearing strain. Right. Now, shearing happens only because of tangential force applied to the surface. Now, I can see that there is a relative displacement, okay, relative displacement of delta x. So, where you can see that in the previous diagram. So, because of the tangential force applied in this direction, right, this is the, I'll write tangential force. Whenever you apply a tangential force in this direction, there is a relative displacement, that is delta x, between the opposite faces of the body, right? So the strain produced because of this kind of movement is called as shearing strain. Now how to measure this? It is defined as the relative displacement, that is delta x, how much it changes divided by its original height. Okay, so we define this in a slightly different way. So let's try to define this. So it is the ratio of relative displacement of a face. So relative displacement is delta x in the diagram. Okay, this ratio of this to the height of the object. Height in the diagram, this is y, okay, of the object. So you know that we can measure the shearing strain as the ratio delta x by y, but from the diagram it is very clear that if you measure delta x to y, that gives you the tan of this angle theta. Tan theta is opposite by adjacent. Okay, opposite is delta x, the change is only delta x, and height of this object is still y. Okay, so I can actually write this is equal to tan theta. Okay, so but if theta is very small, tan theta is theta only. So I can also, some of the books may say that theta is equal to delta x by y. That's also true for smaller angles. Okay, right, now let's go to the third type of strain, that is called as volumetric. This is volumetric strain. So how do you define the volumetric strain? So this is something like, if let us say that we apply certain forces and the forces are being applied normal to the surface. There is an object and we are trying to apply the forces normal to all of its surface. Okay, so in such condition, because of the forces being applied normal to all the surfaces, every surfaces will go change, right, change in their uh, dimensionality or their positions or the area, because of which the total volume will change. So whenever the volume changes, we call that strain developed inside the body to restore it into the original volume is called as the volumetric stress, and change in the total volume is referred to as the volumetric strain. So let's try to write the definition once. That is, uh, okay, if forces are applied normal to surface, applied normal to the surface of a body in, say, all the directions, then what happens? It undergoes a change in its volume. Okay, now if I try to take a ratio, the ratio of change in the volume, let's denote that as delta V. Okay, the change in the volume delta V to the original volume, that is V, right? This ratio is called the volumetric strain, right? So now let's try to understand the same thing with the help of a diagram. Okay, okay, now let's try to, okay, consider this particular diagram in which you can see, right, the original shape is dotted boundaries. That was the original volume V. Now every surface is getting a force denoted by F. Okay, V is the original volume, so the delta V, right, is the change between these two. So if I want to calculate the shearing strain now, therefore not shearing, my mistake, it's a volumetric. Therefore the volumetric strain should be equal to delta V by V. That's how we define the specific volumetric strain of a body. All right, let's proceed further. Then we have the stress and strain of a body can be related to each other by one important law, that is called as Hooke's law. This is called as Hooke's law, right? It actually states that the stress is directly proportional to strain of an elastic body. Okay, so or you can say that stress by strain is a constant. Okay, so this is within the elastic limits of a given body, the ratio of stress to strain is a constant. In the sense, whenever you apply an external force to any body, right, whatever is the internal force developed to the change in its shape per original shape, that ratio, whatever you call, right, that is a constant. That's what is the statement. So according to Hooke's law, this is stress of a body divided by the strain, okay, is a constant. This is the meaning of the Hooke's law. Now, this ratio is actually called as modulus of elasticity or elastic constant. Okay, it actually depends upon what is called as the different material characteristics, right? If it is a perfectly elastic, you have a specific ratio. If it is not elastic, or no, if the material is non-elastic or inelastic, right, it's going to be a different value. Okay, so this constant is what is called as the modulus of elasticity. This is the first name, or also you can call it by another name, that is called as elastic constant. Okay, it's called by these names. Okay, now let's define few more things. So whenever you take such a ratio, okay, linear stress to linear strain, you call it as by a different name. Okay, let's define that term now. This is called as, it's Young's modulus. This is normally denoted by letter capital letter Y. Okay, this is capital Y. So how do you define this? This is the ratio of linear stress to linear strain. So it's a stress by strain only, but it is linear or the longitudinal. So longitudinal, or in bracket I can write linear. Okay, linear stress of a body to the same linear strain of that body, right, within the elastic limits. This is called as Young's modulus, right? So we know that the Young's modulus is nothing but stress by strain. So stress is given by force per area, and the strain is, it's something like length by length. So they will cancel. So the unit will be, right, this implies, what's the unit? Newton per meter square is the unit. Okay, now this basically represents a large force to produce a small length in the small change in the length, right? That's what is the physical significance of Young's modulus, right? So if you have y value is large, implies, if this y value is large, this is going to imply that large force is required to produce a small change in length. So for example, such materials are uh, all metals. Okay, this is iron, steel, copper, aluminium, etc. So you see that they have a very huge Young's moduli. That's just because you need to apply a huge amount of force to bring small change in the length of those materials. So Young's modulus gives you an idea that how much force you need to apply to change its length by a small quantity, delta L by L. Force required per area for delta L by L. Okay, that's the first modulus we define today. Then the second coefficient of modulus is referred as the rigidity modulus. This is rigidity modulus. So the notation for the rigidity modulus is a small letter n. So now we saw the linear stress to linear strain. Okay, but now we try to define the shearing stress to the shearing strain. So this is the ratio of shearing stress to the shearing strain. So N is equal to, normally you see that the numerator is force per area divided by denominator. Now you can either write tan theta, or this is also approximated to F by A divided by theta itself, because right, we use one property from trigonometry, right? If theta is small, this implies the whole tan theta can be replaced by theta itself. So this is the very basic uh, property or trigonometrical identity. Tan theta is theta for theta value being very small. Okay, let's recall what we have done so far. In Hooke's law, we are trying to relate the stress and the strain of a given body. Okay, we apply certain amount of force to a body and we want to see what is the effect, how much strain is there internally. So the Hooke's law states that within the elastic limits of a given body, right, the ratio of stress that is developed inside the body and the resulting strain of the body, that ratio if you take, it's going to be a constant. So stress divided by strain of a given body is always a constant. This is the statement. So what is stress? Right? Whenever you apply some force to a body, right? Internally there is a force developed per unit area to restore the shape. That's the first thing. That's the stress. Divide that force per area whole divided by strain. In the sense, change in the dimension of a body to its original shape. Whatever is that, it's a strain. So that ratio will be a constant as mentioned by Hooke's law. Now, when we take a ratio, we get a constant. So that constant has several names. So you can see that one of the name given to that constant is modulus of elasticity. Otherwise, you can also call the same constant by another name, which is elastic constant. So we can use these two names. Now, depending on what type of stress you are generating inside a body, divided by what type of strain, right? Depending on the types of stress and strain, you have different names given to the constant. So the first name given is Young's modulus of a body. This is denoted by capital Y. So if you take the ratios of linear or longitudinal stress of a body to the linear or the longitudinal strain of the body. So stress by strain is same, but it's longitudinal stress by longitudinal strain. Okay, how much, right, force is developed, right, longitudinally per area divided by what is the change in the shape length per or unit length, original length. That's what is called as strain. Okay, linear strain. So you can see that the y has the following limits, following units: f by a divided by length. So length by length will cancel because it's the same unit. F by a means force is newton, area is meter square, so newton per meter square is the unit of the Young's modulus. So now, what is the significance of this particular number y? Because you can calculate this value for several objects. Okay, for many objects we can actually calculate this y, right? If this y value is large, right, you calculate a y for a given material and you measure the value, means if at all you find that this is a large number, y value, for example, aluminum is very large. What is the meaning of that? It means you have to supply a very large force to produce a very small change in the length of that particular material. So aluminum, copper, steel, iron, etc. require huge force to change their shapes or change their length. That's why the Young's modulus of those metals are very high. At the same time, if you find this Y very small, you require a very little amount of force to change their length. Plastic. Okay, exactly. Then we go to the next ratio. It is called as rigidity modulus. Now, what is rigidity modulus? We'll see. Uh, First, it's denoted by small letter n. So how to calculate? It's the ratio of shearing stress to the shearing strain. So when I say shearing stress, it's obvious that it has to be applied tangentially. So tangential stress to the shearing strain. So stress is once again force per area. The numerator is F by A. Denominator is a unitless quantity denoted by tan theta. Right. But we use a identity from trigonometry. It says that I have written this in the red color here. If the theta is a very small quantity, then tan theta can be approximated to theta itself. Tan theta equal to theta for very small angle, right? So some of the books will also refer this as f by a whole divided by theta. Doesn't matter. So what is the unit of this? I can see that the unit is still mentioned as Newton per meter square itself, because denominator has no this thing, no unit. It's a unitless quantity. Tan theta is a unitless quantity. Okay, fine. Then we go for the third type of the modulus. It is called as the bulk. It's a bulk modulus. So bulk modulus is denoted by K. Okay, so how to calculate? We'll see now first. So this is the ratio of normal stress, normal stress to the volumetric strain, right, of a body within the elastic limit. So K can also be having the similar notation. This is force per area divided by, this is V by delta V, correct? So you know that, right? V by delta V has the same unit, so you still have the units measured for this as Newton per meter square. Okay, now we have another notation for this, right? There is what is called as a Poisson's ratio. right? Poisson's ratio is normally defined in the lateral strain to the longitudinal strain. So there is a ratio called lateral strain to the longitudinal strain. Let's try to define that now. So this is called as Poisson's. This is Poisson's ratio denoted by say sigma. Okay, this is nothing but the it's the ratio of lateral strain, in the sense change in the area, change in the dimension in one direction, that is delta x by x, lateral strain to the longitudinal strain, right? So normally this is denoted sigma is equal to this is beta divided by alpha. So now I'll tell you what is this beta and what is the alpha. So here this alpha is nothing but change in the length per unit length per unit stress in the direction of the stress. So in the direction of stress, how much you have change in length per unit length. So this is change in length per unit LEN per unit length in the direction of stress, right? Along the direction of stress, same direction as that of stress, how much the how much the magnitude changes is what is this. Okay, similarly beta is nothing but you can see that this is the lateral strain. So we can define that it is decrease in the length per unit length direction perpendicular to the stress. So I can still call this as a change in length per unit length perpendicular to the direction of stress. So stress applied in one direction perpendicular to that, how much change in length takes place. All right, so that's how we define the two quantities. Now we need to go for a specific derivation. So the derivation is expression for this bulk modulus K in terms of alpha and beta. That will be the next step. So this is the expression for bulk modulus K, all right, using alpha and beta. Okay, now let us consider a diagram first. Okay, so let's consider this diagram. Now let us say that this cube has area, right, as 1, right? So let the see the cube is, there is a cube here, that is ox, oy, oz, those are the three surfaces, and other three surfaces on the other side, right? So you can see that this is a perfect cube, and let the volume of this cube be 1. Okay, so let's write that first. Let the initial volume of the cube be 1 unit volume. And now let us say that the cube is subjected to three different stresses. They are tensile stress. Okay, so let there be three tensile stresses: Tx, Ty, and Tz. So Tx, Ty, and Tz are the different what you call tensile stresses, right, along, right, x comma y comma z directions, or x y z axis. Right, now the meaning is that Tx will produce change in the direction along x axis, that is Ox. So Tx, this is going to change uh, the length along which direction? Ox, because it is in the x direction, right? So whenever this happens, what happens to Ty and Tz? And Ty comma Tz compress along Ox, but Ty will change the length in y direction, whereas Tx Tz compress along Oy. Okay, so that's the basic concept. So along x-axis, the particular tension, if it is x-axis, Tx will increase the length, Ty and Tz will decrease the length. Similarly, if you go for the direction y, Ty will increase, the other two, Tx and Tz will decrease. Very similar to that, if you go to the z direction, right, Tz will increase, Ty and Tx will decrease. This is what is the meaning of this. So let's write that now. So Ty means increases length along Oy. So during this, Tx comma Tz decrease. So decreases along specific direction. So decreases along Oy. So similarly, I can write this is Ty. Okay, this is a y. So similarly, Tz, it actually increases along OZ. So during this, the Tx comma Ty decrease or compress, decrease along OZ.